Hello, thank you for listening to my talk. I'm Takaya Matsura. This talk is about finite-size security of continuous variable QKD with digital signal processing, which is a joint work with Kento Maeda, Toshihiko Sasaki, and Masato Kowashi. Before going into the detail, let me summarize our results. In this work, we construct a test for fidelity to coherent states by heterodyne measurement. And by using this fidelity test, we provide a complete security proof for binary modulation CVQKD. This security proof, as well as fidelity test, has affinity to digitized signal processing, such as bin homodyne and heterodyne measurement. So this may provide a possibility for resolving digitization problems in continuous variable QKD. Our work is also developing, so there's lots of rooms for potential improvement. So let me move on to the introduction. There are two main types of QKD protocols. First one is called discrete variable QKD, which uses a photon detector. So the outcome of the measurement is digitized. Another type is called continuous variable QKD, which uses homodyne and heterodyne measurement as a detector. So the outcome is analog value or continuous variable. These two have distinct advantages. For discrete variable QKD, they enables long distance communication and robust against noise. But in general, photon detector is expensive and difficult to implement in practice. On the other hand, the detectors used in continuous variable QKD has established technologies because they are also used in current classical optical telecommunication. So these technologies can be applied to continuous variable QKD, but they are fragile against noise. In terms of security proof, the proofs of discrete variable QKD is much matured because most of the protocols can be reduced to the analysis of qubit protocols. And using the idea of error correction, these qubit protocols can be proven secure. On the other hand, continuous variable QKD, the security of continuous variable QKD is difficult to prove. And actually, most of the protocol doesn't have complete security proof in finite size case. Continuous variable QKD also has two different types, which differs in encoding or modulation. The first type is called Gaussian modulation protocols, which modulates amplitude and phase of the coherent state with continuous Gaussian distribution. Due to the intrinsic symmetry of continuous symmetry of encoding as well as detection, these protocols can be proven secure in finite size case. But actual signal processing cannot realize continuous modulation nor truly continuous valued measurement outcome. So at some stage, digitization of signal processing is needed. But incorporating digitization in the proof is difficult and not has been achieved. Another types are called discrete modulation, which uses few constellations of coherent states, typically 2 to 4. These protocols are most easily implementable, but proving security of these protocols are much difficult than Gaussian modulation protocols because they don't have explicit symmetries, which simplifies the proof of Gaussian modulation protocols. In our work, we provide a complete security proof for a binary modulation protocol based on the fidelity test. And this fidelity test can be directly extended to the digitized signal processing. So this may offer a possible way to resolve digitization problem also in Gaussian modulation protocols. So let me explain our fidelity test. For a given state law, we perform heterodyne measurement. And with the outcome omega hat, we can obtain the band, lower bound of the fidelity between low and arbitrary coherent state beta with the following theorem. Let m be an odd positive integer, and let r be positive real numbers. Then we define test function lambda mr like this, where L denotes an associated Lagrange polynomial of the first kind. Then with the outcome omega hat of the heterodyne measurement on low, we obtain a lower bound between the lower bound of the fidelity between low and coherent state beta with the expectation value of the value of test functions. What is important in this fidelity test is that the function lambda has bounded range. So we can use various kinds of concentration inequalities and evaluate the deviation from the expectation value in finite number of trials. The parameters m and r of the test function lambda, it means that if these values get larger, then inequality becomes tighter. But at the same time, the range of the function gets larger. So the convergence speed to the expectation value in the finite number of trials gets slower. Another important point of our fidelity test is that we can explicitly obtain write down the behavior of this test function. So we can extend our fidelity test easily to the bind heterodyne measurement case by simply picking up the smallest value of the test function in the given bin. So by using this fidelity test, we propose an binary modulation CBQKD protocol as follows. Alice modulates the phase of the coherent states according to her binary number, and Bob switches 3 types of measurement: signal, test, and trash. In signal round, Bob obtains shifted key or announces failure. In test rounds, Bob performs a fidelity test explained in the previous slide, and in the trash round, Bob does nothing and just discards the signal. The ideas of security proof of this protocol is like this. It is already known that for pure loss channel and with a suitably weak signal, the binary modulation protocol of this kind can be made secure. Intuitively, we can also prove the security if the channel output low is sufficiently close to the coherent state. Making this intuition rigorous, we made a reduction of the protocol, the qubit protocol, and combining the information obtained in test and trash rounds, we bound the error on this introduced qubit. And if once we can evaluate the error on this qubit by using the techniques known in discrete variable QKD QKD security proof, we can complete the security of this protocol. So in order to explain the reduction to qubit-based protocol, we need to explain what we do in signal round. In signal round, Bob performs homodyne measurement and obtains a real number. If the absolute value of this outcome is sufficiently high, which lies in this acceptance region, then Bob accepts the signal and defines his shifted key by its sign. But this procedure is equivalent to applying this quantum operation to define qubit, and immediately after that performs 0-1 basis measurement on this defined qubit. In this way, we can define the qubit which corresponds to the Bob's bit value. And by combining test and trash round, we can evaluate errors on this qubit. Finally, we show the numerical simulation of the key rates of our protocol. Horizontal axis of the figure shows the attenuation rate of the channel, and vertical axis shows the key rate of this protocol. Different values of Guzai shows the different values of excess noise, which is the source of infidelity. We can show that the key rate rapidly decreases with respect to the attenuation rate. This behavior is anticipated by asymptotic analysis made previously, but our protocol is more robust against the excess noise than previous research. This is not a contradiction because our protocol is not the same as the previous one, which is only effectively the same in the asymptotic limit. So we can also point out that our work has lots of rooms for potential improvement, both in terms of performance and practicality. First, in the field of CVQKD, it is known that four-state protocols have better performance than binary modulation protocol. And our fidelity test can be applied to arbitrary number of constellations. So applying our fidelity test to four-state protocol and complete the security proof will result in a fairly good performance CVQKD protocol. In addition, our proof is for simplicity based on stronger requirement than secure key extraction. So using necessary and sufficient condition for secure key extraction in our analysis, we improve the performance of our protocol. Finally, in terms of practicality, in our protocol, Bob switches heterodyne and homodyne measurement. But using only heterodyne measurement is desired in terms of implementation. So this is under consideration. In terms of more fundamental level, our proof approach is very different from conventional CVQKD security analysis. So comparing these two will be important. So in summary, we develop test for fidelity to coherent states by heterodyne measurement. And by using that, we obtain a complete security proof for a binary modulation CVQKD. This proof technique, as well as the fidelity test, has wide range of applications. So thank you for listening.